Hello everyone, am I audible? If am I audible, please write yes in the chat box. Okay. So okay, great. So let's start. So IICPC is a Inter-IIT Competitive Programming Conclave, which is unites by allied competitive programmers, and we got support from almost 40 plus IITs, triple ITs, NITs, and BEATS, and many others universities. And IICPC is like we hosted a summer camp, and our goal is to host it for free. And the managing team is Ayush, Aditya Misra, and Gauris Baliga, and we have many others members and session holders. And it never been possible if there were not a gold sponsor like AlgoZenith and 0xPPL. So AlgoZenith is a premier platform for internship and placement preparation. The key note of the AlgoZenith is like many students from Tier 3 and non-CSE department got top tier companies like Google and Microsoft and many others great companies. The founder of AlgoZenith is Vivek Gupta, who is competitive programming enthusiast, ex-Googler, and who took first session of the IICPC summer camp, which was on dynamic programming, and you can watch that session in the YouTube playlist. And our second sponsor is 0xPPL. 0xPPL is a next generation crypto and Web3 platform. The 0xPPL is famous because of the founder who is Prasanna Sankar. Prasanna Sankar was India rank 1 in his time on Codeforces, top coder, ICPC, Google, CodeJam, everywhere. Prasanna Sankar founded a company Rippling, which is a 10 billion plus dollar valuation. And 0xPPL hired many great competitive programmers and ICPC world finalists. So if you are excited to join the 0xPPL and you are excited to explore career opportunities in startup, then you can reach out to Prasanna Sankar via his email prasanna at 0xppl.com. And so now let's start the session, which will be covered by Mohit Agrawal, who is master at Codeforces and currently a Googler. So Mohit will take over from now on.
Yeah. Uh, Hello, everyone. Yeah. Hello, everyone. I'm myself, Mohit Agrawal. I'm currently a master at Codeforces, and I'm currently interning at Google. And today, I'll be your mentor for graph theory. So, without further ado, let's get started. Um, what are graphs? Anybody has an idea what graphs are? I, I guess I guess some of you know what graphs are, right? So basically, graph, like formally, if you wanted to define graph can be denoted as a pair of G, V, comma E, where V is the set of vertices and E represents the edges. Like edges can be thought as the connections between the vertices. Now, why are we studying graphs? So like there are a lot of problems that can be modeled using graph theory, like let's say the shortest path problem. And like whenever there is some sort of connection between two or more entities, then the problem more often or not, that can be modeled as graphs. So let's say, what are the types of graph? So there are a lot of type. There are some types of graphs. There is undirected graphs, directed graphs, and weighted graphs. Let's switch to Xcari for now. Uh, so we have some sort of graph, and this right here is called node. this is also a node, and this is an edge. There are multiple types of edges, right? There is, like, in this case this is undirected edge because the edge has no direction associated with it. We can also have like a directed graph, like, so that's why it's called like a undirected. The previous one I saw is called an undirected graph. We can also have a directed graph which has like nodes, and there are some connection between them, and these connections are directed, like they have direction associated with it. So this right here is some sort of directed graph, right? This is directed graph, and the edges there we have here is directed edge. Like, more often or not, the graph we get is like weighted graph. In weighted graph we have uh, edges, but they also have some extra information associated with it. These informations are like weights, like, let's say 3, 4, 5. In different problems these weights can different mean different thing. Like, in some problems they represent like the how strong uh, like the connection is. Let's say in pathfinding, in the shortest path problem, we can have nodes which represents the cities. Like, let's say this is Delhi, this is Mumbai, and like there is some, I don't know what's the exact distance, but let's say it's around 500 kilometers. I may be wrong. That's completely imaginary. Like, and then there is, like, let's say Bangalore. I don't know what the spelling is. And let's say this distance is like around 1000 kilometers. So in some problem, in the shortest path problem, these edges can represent the distances, and the nodes can represent the vertices. So so these are the types of graphs we have. Now, how do you represent a graph? So there are namely three ways in which we can represent graphs. One is adjacency list, another is adjacency matrix, and the third is edge list. So, like, these are the methods in which we store a graph inside like a computer. Like, computer cannot understand these images, right? So we have to store in some form or another. So what we do in edge list, let's say I have an example here. Let's consider this graph only. uh, yeah, this graph. In this graph, uh, what we have is, there is one in adjacency list, one is connected to 2 and one is connected to 3, and 2 is connected to 3, 2 is connected to 1, like we have some connections like that. So in adjacency list, what we can do here is we can write that 1 is connected to 2, and 1 is connected to 2 and 3, and 2 is connected to 1 and 3, and 3 is connected to 2 and 1, and 4 is connected to 3, like this. So this is the adjacency list representation. uh, that's what we have in the slide, that 1 is connected to 2 3, 2 is connected to 1 3, 3 is connected to 1 2, that's that sort of thing. We can also represent the graph in form of adjacency matrix. So in adjacency matrix kind of ways, like we have we represent vertices in rows also and in columns also. So what we have here is, mm, C, 1 is connected to 2, so we have the entry this this entry, this in the first column and in the first row and in the second column, we have a 1 here that represent that there is an edge from 1 to 2. Similarly, we have a 1 here from 1 at the first row and at the third column that represent that there is an edge from 1 to 3. And this matrix is symmetric matrix. That means that if there is a 1 here, there must be a 1 at symmetrically opposite side. So that's how we represent in adjacency matrix. And third thing, we can also represent graphs in form of edge lists. So edge list is like a very simple way. We just list down all the edges that are present in the graph. Like there is an edge from 1 to 2, 2 to 3, 1 to 3, and 3 to 4, like that sort of thing. So out of all these three ways to represent a graph, uh, the one thing you'll find the most is that one thing you would find the most useful is the adjacency list. You'd be using adjacency list a lot in like every single problem. You would be using adjacency list only. There are some instances of adjacency matrix and some instances of edge list also, but they are in like very specific problems. You won't be using these two as that much. So after all of this, like we know how to represent graph now. Now, how do you traverse a graph? So we have an algorithm called depth first search. Yeah, sorry. So what we do in depth first search is, uh, let's say we have a graph, some sort of very complex graph, and we want to traverse a graph. Traversing means we want to visit every single node, and by visiting we want to solve some graph problem. Okay, so how do we do depth first search? What we do here is, let's label these vertices. This is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Let's label these. uh, what we do here is we pick one vertex as a starting point, and what we do is we out of its adjacency, like there is like 2 and 3, and this one also, let's call it 7. The adjacency of 1 contains 2, 3, and 7. What we do is we pick any random edge that goes from 1. We can, let's say for this case, we go to 2, right? And we mark these 2 as visited, like we have visited these 2. Now we explored all the edges adjacency. I mean, we will explore the adjacency of 2 now, but there are no further edges down there. So we will go back to 1 now, because we cannot explore 2 any further now. So now we again repeat the same process. We have to find an edge which is in the adjacency of 1 now. We have already visited this 2. So let's say we go to now 7 and we visit this. So let me write the order: 1, then 2, then we went to 7, and after that, we will explore 7 further. Let's say we went to 5. Okay. Now from 5, we want to explore 5 further. So from 5, we can go to 3 and we can go to 6. Let's say we went to 3, and from 3, we went to 6. Now we cannot explore 6 any further, so we will track back to 3. Okay, and for 3 also we cannot explore 3 any further, we have already explored 6. So from 3 we'll track back to 5, and from 5 we also have covered all its subtrees, so we'll track back to 7. And after that we will there is one more edge we can explore, that is 4. And the next thing we have to write is uh, 4. And we have already visited all the vertices, so that's it. Our DFS is complete, and the order we have gotten is 1, 2, 7, uh, 5, 3, 6, and 4. That's the order we have got. Now, how do you implement this? So, okay, let's talk about the space and time complexity first. So, I'll explain it for after we explain the code also. So, uh, we do DFS. We will implement DFS recursively. What we do is we have a function called int DFS int u, where we want to start with u. And what we do is we first mark u as visited, and we will explore all of the adjacency of u, and then we will recursively call DFS of v if this is not visited, right? So that's how it goes. So let me write in it again on a very simple graph this time. Let's say this very simple graph. We also have a visited array. We have 4 vertices. Let's make it of size 4. 1, 2, 3, and 4. Now, what we did is we first called DFS of 1. So what we'll do is we mark this 1 as visited. So this will be 1, and we will explore the adjacency of 1. So let's first of all let's draw the adjacency list of this. So 1 has uh, 2, 3, and 4, and 2 has 1 and 3. uh, 3 has 1 and 2, and 4 just has 1. So that basically is our adjacency list. So we would let's say we have column DFS of 1. DFS of 1. So we'll first mark this 1 as visited. We'll go pick one vertex from its adjacency. Let's say we have gotten to 2. So we will call now DFS of 2. After calling DFS of 2, now the vertex 2 will be visited, and now we will explore the adjacency of 2. Now the adjacency of 2, okay, we mark this 2 as visited. Now the adjacency of 2 contains 1, but we don't go to 1 again because we have marked this 1 as visited. So that's why we have a condition that if like that's why we have here, that's why we have a condition that, like, let's say we mark this u as visited, and in the adjacency of u, if v is not visited, then only we call dfs of v. Okay. तो हैंग कर दिया। Literally. Restart. Okay. Okay. स्ट्रीम चल रही है। हाँ. Okay, so I guess screen sharing बंद करना stop sharing करता हूँ. I'm so sorry we have lost you there. Uh, that was some sort of technical glitch. So let's just continue. What I was explaining is that I was dry running this DFS, right? Uh, So we have visited one, then we have visited two. Now from two, we want to explore the adjacency of two, but we don't go back to one because one is already visited. From two, we will go to DFS of three because that's the next thing, right? And we will visit 3 and mark this 3 as 1. And now from 3 we see that in adjacency of 3 we have 1 and we have 2, but we see in the visited list that 1 and 2 are both marked as 1, so we don't call DFS on 1 and 2 again. Rather, we will track back to 1, backtrack to 2, and then from 2 we also don't have anything else to explore, so we will track back to DFS of 1. Now from DFS of 1, after that we see that in the adjacency list we have 3, but 3 is already visited, so we will go to 4 and mark this vertex as visited. What we see here is, like, if we trace back this DFS calls, like that gives you a very interesting thing. Like we first call the DFS as one, and the uh one call a DFS to two, two call a DFS to three, and thereafter one also called a DFS to four. uh like, see, and this gives you a very interesting thing, like this we call this as a DFS tree. Why is this interesting? We will see. This is like because trees are very easy to understand and visualize. By running a DFS on a seemingly complex undirected graph, we got a very simple tree, and we call this tree as a DFS tree because we got this after running a DFS. And this edge is called a tree edge. Now, if you see here that there are only three edges, but in the DFS tree there are only three edges right now, because this is not the complete DFS tree exactly. We are missing this 3 to 1 edge, just one this. There is an edge from 3 to 1, like this. This is also a tree edge, and this is also a tree edge, but this edge is, it is not a tree edge, it is called back edge. And this is very important when we study about cyclic detection. For now, let's see another application, what we can do with DFS. There are a lot of things we can do with DFS. One is connected components. We can find connected components using DFS. Like, let me first tell you what connected components are. So, see, in this graph, you see like there are three different things. Don't confuse them with don't say that it's a three graph. It is just a single graph, but it has three components in it. It's not three graphs. Don't get confused. And we see that there are three connected components in here. So using DFS, we can figure out the different components present in the graph. So how do you do that? What we do is we first start a DFS. Let me, so what we do is we first start a DFS on any node in any component. Let's say we started a DFS on one. What will it will do, and we also maintain a visited list, visited vector. What you want to say, and it will, let's make it a little bit larger. It would have seven different cells. Okay, seven different cells. We first call a DFS on one. What it will do is it will visit one, and then it will visit two, but it will not visit any of the nodes in the other components. So what does that mean is we have visited one and we have visited two, and that's our first component, one and two. Then uh, we will run a DFS on another vertex that is not being visited. Let's say from here we have option to pick any of these five vertex. Let's say we've picked three. What it will do is it will visit three, it will visit four, and then it will visit five after the DFS has been completed. And out of all the vertex we have visited now, we can be sure that these three these three, four, and five has are the new addition to the visited list. So that's our another component. And we can also do, then then we call a DFS at 6, and it will visit 6 and 7. And now we have the final component 6 and 7. That's how we can do DFS and figure out the different components in it. uh, so how do you implement it? Okay, that's just a definition of connected components. Two vertices U and V are said to be in a single connected component if there exists a path from U to V. And the concept of connected components is only valid in directed graphs. We are not talking about, sorry, the concept of connected components are only valid in undirected graphs. It does not make any sense in directed graphs. We have called something called strongly connected components for directed graphs. So here is an implementation of how do we count connected components in a graph. What we do is we let's we are using the same DFS function that we have defined above, like the in the above slides. And we have this visited list, and we what we do is we maintain a count of how many connected components we have found. And we go on over all the nodes. Let's say there are total of n nodes, and these are index in this case n would be 7. And let's say the vertices are 0 index, like this is 0, 1, 2, 3, 4, like that. And then what we do is we iterate over all the vertices, and if that particular vertex is not visited, we call a DFS, and which will visit all of the nodes uh, that all of the nodes in the component of which that vertex is a part of, and we increment the answer. And that's how we figure out the connected components in this graph. And like it is true for any single graph, not just this graph. uh, for DFS tree, I strongly recommend you to read this blog. It is written by this FFT. Okay. This blog is very good to get an idea, and I have already taught you the concept of DFS tree. And we'll see why is this DFS tree useful. Let's say we want to figure out uh, yeah, for this graph, this is tree edge, and these are back edges. These are tree edges because when we call DFS to one, the DFS choose vertex 3 and not 5, and it went from let me explain it. So what happened is, when we called DFS to 1, it went to 3, and then it went to 5, and then it went to 7, and then it backtracked, and it backtracked to 6, then 2, then 8, and then it backtracked to 2, and then 4 again, and then it went to 10. And like these the edges shown in dark bold are the tree edges, and this edge, which was also a part of the graph, but this was not chosen by DFS, we call this as back edges. So when we want to detect cycles, let's say cycles, we say that this type of structure in a graph, in an undirected graph. Uh, if we call a DFS, and in the DFS tree, we figure out at that if there exist any back edges, like this sort of edge is a back edge. So if there exists any back edge, we can be certain that there is an cycle, like namely in this case, 1, 3, 5, and back 1 again. 1, 3, 5, and then 1 again. So that's one cycle in this graph. Okay. So how do we detect a back edge mm, in DFS? So what we do is we call. So let me just explain through code only. So I've already explained this. So how do we detect a cycle? So let's say we declared a global variable has cycle equals to false. Now, just like we do DFS, what we do in DFS, we have a parameter u, and we call this DFS on any random given vertex. So uh, what we do is we take in an extra parameter int par, which represents for the parent of u. It's like from which we were called DFS of u. So I'll explain it. Uh, so just like in normal DFS, we mark this U as visited. Just like in normal DFS, we go to the adjacency list of U, and like let's just ignore this line. We don't want to go to the parent. So like if V is parent, we just continue. Like we don't want to repeat. We don't want to go to the same vertex again, and if v is visited, we figure out that there is a package from u to v. So like if we try to dry run this, let's say in this graph, uh, let me get the code also. See, I'll leave it. Okay, so let's say we called a DFS on u. Let's say we want to detect cycles in this graph. What we do is we first call DFS on 1, and we reached one. Like this is the initial vertex, we don't know about its parent. Let's call its parent to be -1, like there is no parent of 1. And then we went from 1, and then we also need to have a visited list from 1 to 12. and we first mark this one as visited. Like we want to detect cycles in this graph, so we first mark one as visited. Now, after calling dfs 1 and minus 1, we check the adjacency of 1. So 1 is connected to 3, 5, 6, and 9. Like as you see in this graph, we are going from 1 to 3. uh, and now, what would be the parent of 3? Like we came from vertex 1, so the parent of 3 would be 1. Now after that, uh, what happened next? What happens is, the visited 3 becomes visited, 3 becomes visited, and we repeat the dfs process. We go from 3 to 5, and its parent would be 3 because it came from 3 vertex 3 itself. And now, interesting thing happens when we are at 5, because let's say we explore the adjacency of 5. First of all, we mark this 5 as visited. Now, what's the condition of back edge? The condition of back edge is simply that, uh, like if there is an edge coming from a vertex u, uh, if there is an edge and it's pointing to a vertex which is not at the parent of this vertex as such in dfs tree, then we can say that this edge is back edge, because the vertex we are pointing to is already visited. This is not exactly true for directed graphs, but for undirected graphs, there are no exceptions to it. So, like when we are at 5, we see that there is a 1 in the adjacency of 5. So, we see that the 1 is already visited. So, we can be sure that this edge must be a back edge. And what do you say after we found a back edge? We say that, like since this graph has a package, we can be certain that this graph contains a cycle. And in this graph, to figure out what the cycle is, we can like just iterate over the path, like from where we came from. Okay. uh yeah. And like that's the implementation. We mark the vertex as visited, we go through all the adjacency of u, and like if v is a parent of u, then we just skip it, because like we don't want to go to the parent again and cause some sort of infinite loop like that. Now, if this vertex v is already visited, what does that mean? That v is not the parent of u and it is visited. This means that, like this means that, uh, for the case of 5, this must be this vertex 1. There can't be any other vertex. Then this means that this is a package from v to u. There is a package and back edge, and that means there is a cycle. That's all. And otherwise, if all of these conditions are false, we call a dfs on v with it the parent of v being u, because like the dfs of u called a dfs to v. Okay. Now, like without going any further, like let's now, how do we detect cycles in directed graph? Now, directed graph is a little bit different than directed undirected graphs. in a way that like these edges are directed. So if we consider the DFS tree of it, like it has not just a tree edge and a back edge. We have a weird edge called cross edge and a forward edge also. So like uh, in this graph, like I've marked it that this is a tree edge, this is also a tree edge, and this is a back edge, this is a cross edge, and this is a forward edge. So what is cross edge exactly? uh, so like we what we see in back edge is that, like, let me just go back to here. What we see in back edge is that the back edge always connect from a node to one of its ancestors. Like 12 connects to 9, 8 connects to 3. So in the DFS tree, 3 is an ancestor of 8. But that is not the case for cross edge. So let's say we call a DFS at 1, it went to 2, it went to 3, it went to 4, and all of these vertices got visited. Now we see there is a backage here because 2 is an ancestor of 4, and it is also visited, but 2 is not the direct parent of 3. uh, Hope that makes sense. So let's say we visited this branch. After that, let's say we go there 1 to 5, now 1 to 6, and now like let's consider this edge from 6 to 3. Now the vertex 3 is visited, but 3 is not in the ancestor of 6. 3 is not the ancestor of 6 if we consider the DFS tree itself. So that's it. That's the differentiating factor between the back edge and a cross edge. That it is an edge from a vertex U to V, which V is already visited, but V is not in the ancestor of U. And crosses does not create cycles, by the way. Neither do forward edges. Only the back edges creates a cycle. Hope that makes sense. So how do you detect cycles in it? What we do for data graphs is we maintain another data structure. Let's say we call it stack. We maintain a stack which represent the ancestor. And let's say we consider this graph, some random graph I'm drawing right now. There is some package from here to here. Let's delete this package for now. Let's say first of all there is an edge from here to here, like this, and then there is an edge from here to here. So let me classify this. So let's say we started a DFS from this vertex. Let's call it 1. Let's number it also. We started a DFS from 1, and then from 1 we visited 2. So this is a forward edge. From 2 we visited 3. Again this is a forward edge. We backtracked to 2 and we visited 4. This is also a forward edge, and from 4 we visited 5. So that's also a forward edge. Now we backtrack to 4, we backtrack to 2, and we backtrack to 1 again. And now we visit 6. And now let's see this edge. From 6 to 4, this we don't want to visit 4 again because it is already visited, but 4 is not in the ancestor of 6. So how do you keep information that like 4 is in the ancestor of 6 or not in the ancestor of 6? So what we do is we create this data structure in stack that contains the information about it. We have 9 vertices. Okay. So what we do is we when we enter a node, we mark it in stack as 1. Like this is inside the DFS tree right now. Like in the DFS stack. Uh, then we visit 2. 2 is also pushed into the stack, and we mark it in stack as 1 because 2 is inside our stack, DFS stack. And then from 2 we go to 3. So we will mark this 3 as 1 also. But now we cannot explore 3 any further. So what we do is we remove this, convert this, uh, we remove 3 from the stack basically. Now what happens is we are from 1 to 2, and these two vertices are only inside the stack. Now we go from 2 to 4, and we push 4 into the stack. So in the stack we have 1, 2, and 4, 1, 2, and 4, and that's the like the DFS stack we have, DFS function stack we have. Now from 4 we go to 4 to 5, and we push 5 to the stack. Now we cannot explore 5 any further, so we remove 5 from the stack, and we track back to 4. Same goes for the 4 here. We cannot explore 4 any further, and we remove 4 from the stack, and we track back to 2, and we remove 2 also. Now we are at 1 again, and now we go from 1 to 6, and then we mark this 6 as 1. But now when we are looking at this edge from 6 to 4, uh, like the all the vertices that are marked in the in stack are the ancestors of 6 basically. In this case 1 and 6 are marked, and that's the only, like 1 is the ancestor of 6. That's all. And if we consider the edge from 6 to 4, it is not, like 4 is already marked, but it's not in the ancestor of this. That means it's a cross edge. It's not a back edge, and that means we don't have a cycle here. And yeah, we see that there is no cycle. And we continue our search further. We go from 6 to 7. We mark this 7 as visited, and this is a forward, this is a tree edge. Now we mark this 7 as 1. Now we go from 7 to 8. We mark this 8 as visited, and we mark this in stack as 1. But uh, like we cannot explore at 8 any further, so we track back from 8 and mark this as 0 again, like this. Now we track back to 7. Now we can explore 9 again, so we go from 7 to 9 and mark this vertex. Now if we want to explore 9, there is this one edge outgoing from 9, and it goes from 9 to 1, and we also push, like we have to push 9 to the stack. Now if we see 1, 6, 7, 9 are in the stack, 1, 6, 7, 9 are in the stack, and then there is this, and there is an edge from 9 to 1. but 1 is already inside the stack. What does it mean? It means that 1 is the ancestor of 9, and there is an edge from 9 to 1. This means that uh, this should be a back edge basically, and we have found a back edge. That means there is a cycle in this directed graph. Let's see how we code that. The package goes from current vertex to one of its ancestor in the DFS tree, which is not the case for forward and back edges basically. No, forward and tree edges, also cross edges. I mean to write cross edges. See, what we have here is an in stack, which like we I've already explained. We again do a global thing. We store a global variable hash cycle, which is initially set to false, and when we detect a back edge in the DFS, we mark this hash cycle as true. So let's see. We first mark this you like when we are doing a DFS. Like you can notice a tiny difference here. Like we don't uh, put a parent parameter in the DFS. We only did that for directed graphs because in undirected graph we can have a cycle of only two edges. Like this is considered a cycle, but in an undirected graph, this is not a cycle. Although we can go from u to v and back again, back forth, how many times, however number of times we want, we can go back and forth. But in the acted graph, this is considered a cycle. So we don't care that if we can go to directly parent again. That's why we don't have a parent parameter. We don't need them. So when we call a DFS to U, we have to do a lot of things. First of all, we mark this U as visited, like we always do in a DFS, and we put it inside a stack. Now, for now we will explore the adjacency of U. Okay. If V is already visited, like let's say V is inside the adjacency of U, and V is already visited. So we can have two cases. Either U to V is a cross edge or U to V is a back edge. If U to V is a package, we can say that it has a cycle. So how do we differentiate between a package and a cross edge? For back edge, V must be inside the ancestor of U. So if n stack of V is true, what does that mean? It means that U to V is a back edge, and we can mark this as has cycle equals to true. And otherwise, if V is not visited, we want to explore the V, and the edge from U to V is a tree edge. And when we leave the vertex, this is important. Don't forget to remove it from the stack, because like we have already explored that node and its subtrees completely, and we have to remove it. That's it, and that's how we detect cycles in a data graph. So before moving to BFS, uh, like I would want you to mark your attendance. Mm, there is a QR code given. I'll give you a 5 minutes break. Uh, Scan the QR code and mark your attendance. We really love your feedback. You will have a 5 minutes break. चलो 8:15 में स्टार्ट कर रहा हूँ। माइक एक्सेप्ट करना। Okay. So till now, can I get a +1 that everybody has understood till now what I have taught in the chat, and a -1 if they think my session was bad. Okay. Okay. We will do one problem here about cycles. It is called round trip. I'll give you 2 minutes to read the problem, and let me. Yeah, you have 2 minutes to read the problem. I'll do the font. Okay. Now let's start explaining the problem. So in this problem, you are given a city, like we are basically given a graph, and it's an undirected graph. Uh, there's there are n cities, there are m roads between them, and your task is to design a round trip that begins in a city, goes over two or more cities, and finally returns to the starting city. What does this means? This means that we want to find a cycle uh, in the graph basically, and that must contains more than two vertices. That is like three vertices, four vertices, stuff like that. Uh, and we in this problem we also have to print the vertices in the graph, like the from where we have found the cycles. So let me draw the graph given in the question. We have vertex from 1 to 3, 1 to 2, from 1 to 2, 1 to 3, and 5 to 3, 1 to 5. 1 to 3, 1 to 2. There is also an edge from 3 to 5. What happened? There is also an edge from 3 to 5, uh, 1 to 5, and 2 to 4, and 4 to 5. Okay. So they are. You can see that there are multiple cycles in it. 1, 3, 5, 3, 1, 2, 4, 5, 1, or 1, 2, 3, 4, 5, 1. Like there are basically three cycles in it, and they have reported 1351 as an answer. Like if there are multiple answers, you can print any solution, right? So how do you do it? uh, what you do is, like, we basically run a cycle detection algorithm, that we try to run a DFS on this graph, and try to prepare a DFS tree, and try to detect a package. Like for this case, let's say the DFS tree comes out to be this. We went to from 1 to 2, 2 to 4, and 4 to 5, and 5 to 3. These are our tree edges, and there is a back edge from, use a different color. There is a back edge from 3 to 1, and there is a back edge from 5 to 1. See, like this. So how do we know how we can detect this back edge thing? But how do we print the vertices in it? So what we can do here is, as soon as we detect a package, we want to print this. So let's say from 5, we detect. Let's use a different color again. From 5, sorry. Let's say from 5, we detect this package. Uh, so what are the vertices in it? So there is this 5, parent of 5, that is 4, in the DFS tree itself, parent of 4, which is 2, and parent of 2, which is 1. And we have reached the vertex which is pointed by our package. And see, these are the vertices in our cycle only. And for this question, we also want to print the 5 again, because 5, 4, 2, 1, and then 5. That completes our cycle. So that's how we can print our cycle. We just have to maintain another array called parent, and as soon as we find a package, we can, like, iterate over the parents, and basically print them. So how we can implement it? uh, like, I have a code already. Like, I will, without wasting a lot of time, I will just show you the code, how we can implement it. Don't worry, you will get the links of these submissions after the session is over. So what we do here, let's see. This part is template, just ignore them. uh, in our main in our main function we just read the number of test cases, but we haven't any. So let's move out to the solve function. In the solve function, we read n and m, where n represents our number of nodes and m is the number of edges, and we basically create an adjacency list out of the. We basically create an adjacency list. How do we create an adjacency list? Uh, what we do here is we store our adjacency list in a vector of vector. Why do we need a vector of vector? Because adjacency list is nothing but a list of lists. For every vertex, we have all the other vertex it is connected to. So in this case, adjacency of I would represent or would have the would represent a vector which basically contain all the other vertices I is connected to. So to read our to read our graph and prepare an adjacency list, let's focus on this loop. Uh, we have m edges, right? We have n nodes and m edges. We what we do is we have to read m edges. So we created a for loop for this, and we read an edge, and the edge is given nothing as a pair of nothing but a pair of vertices. And so in this we are given a and b. This means that there is an undirected edge from a to b. What does an undirected edge means? That we can go from a to b and b to a. So let me read this vertex. In my code I've already we have decremented it, but it is completely optional because I wanted my vertices in a zero indexed manner, like from 0 to n minus 1. So I have decremented it. It's just a matter of preferences. Some people use one based indexes, some people use zero based indexes. I like to use zero based indexes, so I converted it in zero based indexing, and we add an edge from a to b. And because b lies in the adjacency of a, like let me go to that calculator again. So a, and then we have b. So b lies in the adjacency of a, and a also lies in the adjacency of b. So that's why we have to like push it twice. In the a also we push b, and b also we push a. Now, as I explained, we are running a DFS. So what do we always want? We always want a visited array, unless until we are doing a DFS on tree, but that's a matter of another session. But for any graph we are running a DFS on, we have to have a visited array. And as I explained earlier, we want to have a parent array because we want to iterate over all the parents as soon as we find a package in order to print them. So like these variables, we maintain these two variables like which represent where the cycle is starting and where the cycle is ending. Now like let's start with the TFS code. This and syntax might looks complicated, but it actually in a way is useful. Like it's basically a function called DFS, and I used a lambda syntax uh, to represent it. It's nothing fancy. It's just like I write a DFS. You can read more about this syntax later, but let's continue our discussion. Uh, so we are like we were like the way we were doing cycle detection using DFS. In the similar manner, we want the current vertex we are running. We want to explore and the parent of that vertex. Parent is important, and we what we do is we store the parent of current uh, because like the way DFS explores, it somehow creates a some sort of DFS tree, and like parent is the parent of current in that tree. PR is the parent of current in that tree. We want to store it in order to print it later. We mark the current as visited, and now we want to explore the adjacency of current. So what we did is we iterated over every node which is connected to current, And then if this is equal to parent, then we simply ignore it, uh, because we are having an undirected graph. For directed graph, we don't need this condition. And if this vertex is already, if that vertex was already visited and it is not a parent, what does that mean? This means that there is a package from current to iterator. So there is a cycle from current to iterator, and like we maintain these two variables and we return from our DFS. Otherwise, if iterator is not visited, we will continue our search. Like self is basically just a reference to the DFS function. Self is basically a reference to the function, reference to the DFS functions. You can write a DFS like this also. Why write like this? It will save you some sort of typing. You don't need to pass in visited array. You don't need to pass in parent array. You don't need to pass in the adjacency list in the parameter list of DFS. So it just saves some sort of typing. That's all. Okay. And after the DFS is over, what we have here, we will have our cycle from and cycle to set. And like if there is, if these two variables are not set, what does it mean? That we have no cycles. We actually have no cycles in the graph. And basically we want to run our, first of all we want to run our DFS. Like we have created a function of DFS, but it doesn't do anything until we call the DFS function. So we iterate over all the vertex, and if it's not visited, we will run our DFS. That's how like most people call DFS. Because like if we don't do a for loop, and let's say you just called a DFS on a single vertex, what if there are multiple connected components in the graph? Let me explain it here. What if there are multiple connected components in the graph? You explode one component, but you miss the other components because DFS does not reach there. That's how it works, right? Let's say you call a DFS here, it will visit every single node here, but these vertex are simply not reachable from here, so the DFS will not reach here and will not detect cycles here. Cool. Now, after we run our DFS and every nodes are visited in the graph, what we see is, if we see that the cycle from variable is still not set, this means that there is no cycle in the undirected graph. Now we want to construct the cycle. uh, what are the information we have to construct a cycle? We have the cycle from and the cycle to, and there is a package from cycle from to cycle to, and we have maintained a parent array also, which represent the parent of a particular node in the DFS tree. The similar scenario I have discussed in the Excalibur draw, like this. So we start from, we go to its parent, we push this also, we go to its parent, we push this also, we go to its parent, we push this also. We continue doing this until we reach the cycle 2. That's all I did. Like we start from, we push the node and we'll move to its parent until we have reached the cycle 2, with that there is a package from cycle from to cycle 2. And just for the sake of completion, the problem wants me to push these two also, like cycle 2 and cycle from, and now we can like just print the cycle. And we want to add plus one also, because in the problem we are given the vertices in one based indexes, but for our convenience, for my convenience at least, I like to use zero based indexes. I need to convert into one based indexing, and that's it. Hope you enjoyed this problem. Like it was a very basic one. Now, it- with the help of this problem, I also explained how like the implementation of DFS actually looks like. Now it's time for the next topic, BFS. It's also called breadth first search, we can also call it level order traversal. Time complexity of this is same as DFS, which is O of V plus E. Space complexity can go till O of V. Okay, so this is also a graph traversal algorithm. I'll show you how it works. Then I'll show its code and its implementation, and then we'll do a problem in DFS, and we will wrap up. That sound good? So BFS explores a graph, undirected graph, in a way, in a circular, some sort of circular manner. So let's consider some sort of weird graph like this. So let's say we start from this vertex. Let's. I put a number 0 here, means that it 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 has something to do with the distance. Let's say this is the source, and we put a 0 here, means that the distance from this is 0. Now we explore its adjacency. We see that there's this, this, and this in its adjacency. We like, let's say, then we what we do is we visit this one and mark this as 1. We visit this one and mark this as 1. And we don't go in the depth of one. We just visit the nodes that are in the adjacency of this 0. And now we this we like visit this one and mark this one. That has something to do with the distance, because like it has like a distance of 1 from the source vertex, and we mark this as 1 also. That's all. And it basically traverses the graph in a circular manner. We first start here, then we traverse the nodes with the distance of 1, and then we go to one of this one, and explore the nodes further. But for this particular node there is no further thing. For this node, we'll explore this one and mark this as 2. We explore this one and mark this as 2. We don't explore this one because this is already explored. And now we go here and we do the same thing. We mark this as 2. We mark this as 2. And if there was like further down the line in the graph, we would have done the same thing. And in the next iteration, we have marked this as 3. We have marked this as 3, and same for this one also. That's how we do BFS. So, like, intuitively it sounds good. Like, we go from source, we visit its adjacency, then again we visit the adjacency of that adjacent vertices, and somehow we get the distances. Like, this thing represent the distance from 0, something like that. Now, what happens? How do we implement it? The question is. Uh, like, we can what do we do in the BFS is, like, we maintain a, like, we use a data structure called queue. I'm guessing that like, as all of you are here, most of you know what queue is. It's like, first, what queue is, like, the elements, like, you can push at the back and you can pop from the front. Like, in the queue you can push from here and you can pop from here. So how this is useful? Mm, we maintain a queue. Let's make a bigger queue. And in this graph, like, let me draw here. We first of all like, push the source to the queue. Let's say this vertex is let me just label this vertices real fast. I'll use blue color. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What we do is we push the source here, like we push the 1, and that's it. We first of all push the source in the queue. Now, uh, in the first iteration, we will visit all the nodes in the adjacency of 1, and we will pop the 1 from the queue. So what does it look like is we push 2, we push 6, we push 8, and we push 7, and we pop this out in the first iteration. And we also mark their distances as 1, like this. In the next iteration, we go to 2 and figure out its adjacency. Since there are none, we will just pop this out without doing anything. We go to 6, we figure out its adjacency, which are 4. I have not labeled this. Let's label it 13. So when you go to 6, there is 4 and there is 13. There is 4 and then there is 13, like this. And we'll also pop out 6, and we can also mark their distances as 2. Now we go to 8. uh, so in the 8 we have 9 and 10. We'll put them in the queue, and we also pop that out. And for 7 we don't have anything, we'll just pop them out. Now you can see that after we visit that distance of 1, we get the all the vertices in the queue which are at distance 2 apart from 1. Now we do the same thing again. We go to 4, and we push this 3 and 5, mark their distances as 3, and pop 4 out. We go to 13, push 11 and 12, and pop them out. And go to 9, there is nothing there, we just pop them out. And we go to 10, there is nothing there, we just pop it out. And these are like distance 3 apart, these are distance 0 apart, these are distance 1 apart, these are distance 2 apart, and these are distance 3 apart. So like in BFS, we always visit the next vertex which is like minimum distance apart from the source vertex. Like we first visit the nodes which are 0 distance apart from the source. Then we visit the nodes which are distance 1 apart. Next we visit the nodes which are distance 2 apart. Next we visit the distance 3. Next we visit the nodes which are distance 3 apart. And like as you might expect that this BFS traversal is really useful when you want to figure out the distance from a particular source, right? uh, BFS, like it is mainly like there are some several application of it, but the one that I mostly use is the single source shortest path in undirected graph. See, like we use this BFS to figure out it. So we talked about its implementation. Now, how do we code it? Uh, so let me show you the code of it. Yeah, first of all, let's talk about its application. So we use this BFS to figure out the single source shortest path to other vertices in an undirected graph. We can also use BFS to find connected components, because in BFS also, when we run a BFS in a graph which is not connected, it will only visit the vertices which are connected. Like if you run a BFS, this only this connected component will visited. This will not get visited unless until you call a BFS on some other node in this connected component also. That's how it works. Uh, yeah. Now, so we can also use BFS to find connected components. The same way we do TFS. It doesn't really matter that much. Okay. We can also use BFS for Khan's algorithm, like for in topological sorting. It's basically an algorithm for topological sorting that will be discussed in the further sessions, I guess. Now, how do you implement it in the BFS? Like this code is like just taken from CP algorithms. It's not mine. I've just mentioned it like beforehand. Now, how does it work? Okay. We have, let's say we have an adjacency list prepared already, where n is the number of nodes and s is the source vertex where we want to run our BFS. We, as we have discussed earlier, we want to maintain a queue um, for our BFS. Uh, Used is simply visited this, and we have d of n and p of n. P of n, if you want to real, like in most of the cases you don't need p of n, but you, if you want to construct the shortest path from source to some other vertex, like you actually want to know what are the intermediate vertices I need to visit, then p of n really helps. Now, as we have discussed earlier, we first of all push S to the queue, and immediately after we mark S as used, or you can say it's visited. And the parent of S is -1, because this is the source vertex only. Okay, we didn't come to S from any other vertex. Okay. And one thing you see in BFS is that you like immediately mark a node visited after you push that node into the queue. So we run a while loop until queue is not empty, meaning that there are still some nodes to explore further. We, what we do is we pick a top front of that queue, like we have discussed in like we have discussed earlier. We pick the first element of the queue, we pop it out, and we explore its adjacency, just its immediate adjacency, not the further than that. Like we iterate over its immediate adjacency, and if this is not already visited, then we mark this as used or visited. I'll use this term interchangeably for now. And and then we push this u to the queue. Okay. And we increment the distance, like the distance of u should be one more than the distance of v, and the parent of u is v, right? That makes sense. Implementation of BFS is clear. Now I want to discuss a problem on BFS. uh, let's say the shortest route one, like it is this problem. We, like, I'll give you a minute to read, not more than that. It would be just a minute. No, 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 not this problem, not this problem. My bad. Uh, yeah, I'll leave that problem. Yeah, this problem is of BFS. We'll discuss this. Uh, you have 2 minutes to read this problem and think about a solution if you can. It's a really great problem. Okay. Now I would like to explain this problem. Let me copy this test case first. I'll explain this problem via the test case. Let me draw the grid myself. So, so it's 1, 2, 3, 4, 5, 6, 7, 8. 8 cross 1, 2, 3, 4, 5. 8 cross 5 cell. 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5, 6, 7, 8. Okay. We have a monster here. We have a monster here. We have a monster here. And like these are all the walls. Let me use a different color. These are all the walls. Like everything is a wall here. Everything here is a wall also. This space is kept empty, and yeah, and that's our character. What you want to do in this problem basically is we want to reach one of these corners, like one of these corner cells, not exactly corners, border edge, border cells. Like this is a border cell, this is a border cell, this is a border cell, this is also a border cell, this is also a border cell, right? So we want to reach a border cell, but we don't want to get caught by a monster, right? So how do we do that? Mm, one idea is that we pick a path that cannot be reached by, like, that cannot be reached by a monster. Like we just want to pick like we want to pick nodes such that that cannot be reached by monsters. So how do we do that? We can like as the problem says that uh, you take some steps simultaneously in one direction, and your goal is to figure out uh, if the goal is possible. That means that you need to figure out if there is a path uh, from that goes from you to some border cell. So one way to think about is, let's prepare distance uh, in the grid. Like from A, let's prepare some sort of distance. 1, 2, 2, 2. This is hardly reachable. Like I draw it very badly. Let's like redraw it again. And this is last problem, by the way, for this session. After that, we will end it. One, two, three, four, five, six, seven, and just one more. Yeah. And we have a master in this cell. We have a master in this cell. These are all walled. Like from this one, this one, this one, this one to we have walled this one. There is a master here. Dot dot. We are starting from here, and there is also like a wall here. Wall dot wall dot master wall dot wall, and then we have wall here, monster here, wall dot dot wall dot dot. And for the next one, like we basically have all walls here except for the second cell, right? What we'll do here, let's use green color. We first of all run a BFS from our character to figure out the distances to each cell. Like this is one, this is one, this is two, this is two, this is also two. This is three, this is three, this is three. Now this is four, uh, this is four, this is four. Let's not go through master for now, because we anyway will not be crossing the master. That would be very stupid approach. One, two, three, three, four, four, five. Right. That's a just green color represent the distance from A to that cell. Like there is one, two, 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 three. This one is four. This one is four. This one is five. The rest of the vertex are either very bad idea to traverse, or there is a wall to it. We cannot go there. So in this case, and also let's use another color called orange. Um, we also run some sort of multi-source BFS. What does that mean is, we also want to know how much, uh, like when the monster can arrive at that cell. That's all we want to know. Like for this cell is already a monster, that means that's a zero. Like it is monster is here from day zero. Monster can arrive here at time 1. Monster can arrive here at time 2. Monster can arrive, like we do the same thing. There is a 0. Monster can arrive here at first, second. Monster can arrive here at second, first, second, first, second, third, fourth, fifth, sixth. So, how do you know that we can cross a cell safely? Safely, like these both green and the orange ones can be calculated using BFS. How do you know that we can traverse that node safely? When the when the distance from the monster, like this orange, is greater than this green, then we can safely say that we arrive before the monster, and that means that monster cannot hit me right now. So like we are safe to go there. So in this particular case, if you look at this path, like we are here at 0 and this is 1, this is 1 and this is 2, so we can go here. From this is 2 and this is 3 means we can go here. We can also go here, we can also go here, we can also go here, and we have finally arrived at our border cell. That means this is the path. So the answer would be RRDDR. Uh, so RRDDR. So that's the answer. So let's look at how do we implement it. We are basically a short on time, so I'll just show you the code on how do we implement it. As you can see that it's a very big code, but don't worry, it's very easy to understand. Like we take in the input of the grid, we check that if we whether or not we can go to that cell. That basically means that I should not overflow the range. J should not overflow the range. J should be from 0 to n minus 1. I should be from 0 to n minus 1. And like if there is a wall, we still can't go there. And otherwise, if these three conditions are false, we can probably go there, right? So we first of all take input of the grid. We declared a helper function, which helps me whether or not we can go there. And these two arrays are pretty common when you like do any graph search on a grid. These represent the directions we can go. I like to call it as delta x and delta y. That basically means the change in x and change in y. When you want to go in a particular direction, this basically means 1 0. This means basically means one down. This is up. This is right, and this is left. Down, up, right, left. And we created a time matrix, basically which represent the distance. Basically it represent our distance, what we are doing here, from the monsters, right? So what we do is we create a queue. uh, there we store three things. One is the row, column, and the distance. So in multi-source BFS, we don't just put in like unlike in BFS, we just put the source vertex and mark this distance as 0 and we are done with it. But in multi-source BFS, we don't really push a single, but we can push multiple sources in it and mark all of its distances as 0. And what it will do give us is that the optimized distance from all of these monsters, right? We instead of running n number of BFS from each monsters, we just run a single BFS to get the minimum distance to a particular cell from all of the monsters. That's how powerful this multi-source BFS is, and you see that this is a very powerful technique. And like just the way we do BFS we done here, we figured out the row, column, and the distance from the front of the queue. We remove that, and if like this condition is like we are not using a visited array here, you can notice here we are just using a distance here. So like this here, if we already have a better distance stored in our matrix in T, that means that you can be certain that this vertex has been visited before and it is being visited again. So instead of using visited matrix, you can like just reuse the distance to figure out that whether or not that this vertex is visited or not. And if it is not that, meaning that this contains the minimum distance to this vertex, we like set our distance, and like we go to all the four directions, uh, like to go to the next vertex we add the change in x, we in the j we add change in y. And whether if first of all we check whether or not we can go there, that means it's not out of bound or a wall. And if t plus 1 is less than this, meaning like again we are not using visited, and we want to check that when we visit there, we visit there at minimum time or minimum distance as possible. So the distance when we visit new I and new j, the distance should be t plus 1. But if we already have a better distance, then we don't want to visit there. If we don't have a better distance, meaning we have a larger distance stored here, meaning this for cell is probably not visited till now, so we push it in a queue to be visited later. And after this bfs is over, we will have an optimized distance to each cell from each monsters, right? Like we basically calculate what do we calculate, we basically have calculated the uh, orange distances. We basically have calculated the orange distances after we ran our first bfs, right? Now okay, this is different problem. Yeah, see, so after we ran our first bfs, we have our optimized distance. Now we also want our distance to be calculated for the next thing, that is from the player also, right? So we want to like calculate this. So first of all, we iterated over this uh, to figure out the players in it. And we also have a direction matrix. uh, what does this direction matrix contain? It just marks the distance basically. And like we in problem, it's probably given that we have just a single a. But like as soon as we have figured out a single a, we can probably break out from both of the loops, not just one. So like as yeah, we just have single a's, so it doesn't really matter. um, I let this second loop also run forever. Now in this we marked our distance. And now what we do here is we ran our bfs. Like this loop is to just to search where our starting point is. These both of these loops, no, don't get confused. Now we run our bfs again. We have maintained like queue also here, we also have pushed it in the queue. And in the second bfs we do the exact same thing, but this time we are doing it for the a, not for the m, where a is our the like a is the our player. I don't think I need to explain this again, because that is like exact, it is very similar if not exactly the same as this while loop. Now after we have calculated both of the distance, now we actually need to construct our path, right? So what do we do is we go to how do we figure out the path. See, where is, oh, I scanned it off. We can check like see what we are doing in this code. Like I've written this code a long time ago. Let me check. Right. We basically check all of our border points, and if you see that this can be visited before, player can reach this border point before any monster. This means that there probably exists a path for our player to reach our border node. So in this case, see, our green is smaller than our orange, and this cell lies at the border, which means that uh, there is a path from this to our player, and yeah, there is a path, and like this path will give you our answer. So we basically did the same thing. We are doing it in a reverse. You can also do a DFS, that's totally fine, but we have constructed a path like this. Right, like if direction is -1, meaning that like we continue if the direction is -1, that basically means that this cell is probably not visitable by our player. Yeah, because that's how we initialized it. Now we want to construct our path. So until or unless we reach our player, we go to the direction we want to move in. See, this direction, like, yeah, this direction not only contains the distance, it contains our the player also, like where from where we have come here. And right, so we will check whether or not we have reached here, and until or unless we reach our player, from that, like, we are iterating the path in reverse. So we figure out the distance, uh, direction, sorry, we figure out the direction in which we want, we moved there, and like push the symbol in the path, and like we move there. Like it's not very hard to understand. I might made it sound a little bit complicated, but it's really easy. That like if you don't understand this approach, like you can just do a TFS, and you only go to the vertices that have like orange, like this condition fulfilled, in order to reach here. I'll send you the code, send you my code if you want to read it again. Yeah. That's all for my side. I guess the session is over now. You can